Hey guys, today we're doing a lesson on present value of annuities. So basically, after we've saved for retirement or we've done an annuity like we did in the last lesson, you're going to retire and you're going to start withdrawing the money or taking it out. So the amount that we have before we start withdrawing is called the present value of an annuity. It's also like this is also the formula they use for paying back a loan, in case you're wondering. So you can also use this for loans. Can also use this for loans. But we're going to see what happens. So what happens when you start withdrawing money or taking money as an income from that retirement plan that you have been saving for over a number of years. So in this case, there is a different formula. It looks kind of similar, but yes, it is different. And it looks like this. PV, or present value, equals R 1 minus 1 plus I to the negative n. So there is a negative exponent divided by I. So it looks a little bit similar, but there are a few differences. PV is your present value. So it's basically what does the annuity worth today, or what is the loan worth today, present value. R again is your regular withdrawal. Or if you're looking at it as loans, it's your loan payment. Like so your regular loan payment. I, same as last time, interest rate divided by number of compounds per year. So don't forget that this has to be in decimal form, just like we did in the last lesson. And n is the same as well. It's your number of years times the number of compounds per year. Compounds per year. So I'm going to put per year here so that like if it's monthly, it would be 12. Let's look at an example and we'll see exactly how this works. So Mark is converting his RRSP into an income fund. So he's been saving and now he wants to start withdrawing it. He wishes to receive $1,500 every 6 months for the next 20 years, starting 6 months from now. He's guaranteed an interest rate of 6.25% compounded semi-annually. So again, I like to go and highlight what I want. So 1,500 every 6 months, over 20 years, 6.25% compounded semi-annually, so that I can then make a list just like I did in yesterday's lesson, and then calculate and use the formula nicely. So here's our solution to A. So I make the list just like I did before. PV, R, I, and N. So PV we don't know. We want to know how much we need to have right now so that we can pay for the annuity. R is our regular withdrawal or payment, and it is $1,500. I, 6.25%, so I'm going to put that in decimal form, 0.0625. And we're going to divide by how often. It's semi-annually, which is twice a year. So we're going to divide that by 2. And N is how many years? 20 years, which I got from up here. And we're going to times it by 2. That one's easy. It's 40. And I'll just do this calculation. 0.0625 divided by 2 which is 0.03125. Once you have all of those numbers, we've got 3 numbers and we're looking for PV. We'll use the formula. PV equals R 1 minus 1 plus I to the negative n. Don't forget that negative on the exponent divided by I. So I'll substitute all the values in. 1500, 1 minus 1 plus 0.03125 to the negative 40, all divided by 0.03125. Again, don't round anything because we don't want to round until the very last step when we have finalized everything. And also follow BEDMAS just like we did yesterday. So I'm going to do what's in the brackets first. This is 1.03125 divided by 0.03125. I might run out of room here, but that's okay. 1 minus, I'm going to do the exponent on that. Now don't forget to put the negative on the exponent. To the exponent of, so there is a negative sign on most scientific calculators. Don't use the minus sign, use the negative sign. So I put negative 40 as my exponent, and I got 0.278225919. Again, do not round it. 3125. We're going to finish the bracket off. 1 minus 0.278225919, which is 0.721774081 divided by 0.3125, and then we're going to multiply and divide. Divided by 0.03125, and I get 34,645 and 16 cents, because this is the step where we can actually round. So that means that if he wants to take out 1,500 every 6 months over 20 years, he's got to have at least $34,645.16 saved or put into that account so that he can do that. Let's go to the next page and I'll show you how we find R. Alright, so similar to annuities, we can use this formula to find out how much we can withdraw on a regular basis, which is kind of more like what you'd want to do because we've saved all this money and we know how much there is. So it's kind of good to get an estimate of what can I actually take out for how long I think I'm going to need to take it out for. So if we know what we start with, we just have to rearrange the formula and it will look like this. R equals PV times I over 1 minus 1 plus I to the negative n. Okay, so it's just been rearranged. Let's see how this works with an example, and then I'll let you guys do the practice stuff. Alex has $60,000 saved in her RRSP. She will use the money to buy an annuity that pays 6.8% compounded semi-annually. She will receive semi-annual payments for the next 25 years. Again, guys, highlight what you can. Compounded semi-annually, 25 years. The first payment will be paid 6 months from now. Determine the semi-annual payment she receives and determine the interest earned during the term of the annuity. So I think I forgot to find the interest on the last example, but that's okay because we'll do it with this one and it works similarly to what we did yesterday. So A, again, let's make a list and do some of our calculations first. So we've got 60,000. That's what we have right now. R is what we're trying to find out. I, 6.8%, so 0.068 divided by 2 because it's semi-annually, and then 25 times 2 because it's semi-annually. So 50 times 0.068 divided by 2 is 0.034. And so we'll substitute those values into our formula, which was PV. No, what am I doing? Which is R PV times I divided by 1 minus 1 plus I to the negative n. So 60,000 times 0.034, that's on top, and the bottom 1 plus 0.034, so I'm just going to add it right now. Sometimes I like to skip that step. Minus 50. Let's deal with the top, deal with the bottom, and then we will divide it. So 60,000 times 0.034 is $2,040. And then the bottom 1.034 to the negative 50. So make sure you put a negative on that exponent. I get 0.187920025. We'll subtract that and then we will divide. 1 minus 0.187920025 divided by 0.8120799975. So again, don't round it, and then we'll do our division. Divided by 9975, and I get $2,512, and now I can round it, so 7 cents. Okay, the last thing you're going to do, B, is how much interest was earned. So if this was the payment that you get to get, let's multiply it by how many times we get it. So 2512 07 times 50. 251207 times 50 is $125,603.50. And then our interest is the difference between that and what we started with. So we'll subtract them. 603.50. It looks like it's more than half, which is crazy for, see how much interest you guys earn by like basically doing nothing. You just let the money sit there, which I know is sometimes hard, but you earn more interest than what you originally had just by letting it sit there. So all that money that you're getting, $65,603.50 is interest that accumulated while it sat there, while you just took a little bit out at a time. Loans work exactly the same way with both of these formulas. So you can find out what what the cost of the loan is and how much interest you'll pay on it. But you can also figure out your loan payments by doing exactly what we just did here. PV would be the amount of your loan. I is the interest rate, how long you're going to take it out for, and then R would calculate your payments. You can kind of figure out like or estimate what you might pay for a car before you actually go in and discuss what you're going to pay for it or how you're going to buy it. So it comes in really handy, this formula, and I really like to use it. So that is it for today. Again, you can use the calculator that I showed you guys yesterday. And then in the next lesson, I'm going to show you another calculator that you can use that's really good for mortgages, but also does loans. So stay tuned for that, and I will be back. Bye, guys.